Okay, so we'll get started with our talk this afternoon. Yeap Kang will tell us about his work on the proof of the Erdos-Faber-Lovasz conjecture. So I'll turn the time over to you.
Thank you for the introduction. And I would like also thank the organizers of the conference. And it's a great pleasure to give a talk here. So today I would like to talk about the proof of the Erdos-Faber-Lovasz conjecture for large hypergraphs. And this is joint work with Tom Kelly, Daniela K, and Abhishek Methuku, and Deryk Osthus. So let me start with some basic definitions. So a hypergraph is a generalization of the graph consisting of a pair V and E, where V is the set of vertices, and E is the multi-set of edges, where an edge is a non-empty subset of the vertex set V. So here are the two examples of hypergraph. And in this talk, the main topic of this talk is about the coloring the edge of the hypergraphs. So a proper edge coloring is the edge coloring of a hypergraph such that no two intersecting edges have the same color. And the chromatic index of a hypergraph is the minimum number of colors in a proper edge coloring of H. So we want to color the edge set of the hypergraph as few as possible. So here is a Peterson graph, so which has a chromatic index 4, as in this figure. And here we have the projective plane of order 2, which has 7 edges intersecting each other. So its chromatic index should be exactly 7. So if we collect the edges of the same color, which we call a color class, then those edges are pairwise disjoint by the definition of the proper edge coloring. So in fact, we can describe proper edge coloring in terms of hypergraph matching. So matching is just a collection of pairwise disjoint edges. And a proper edge coloring is then a decomposition of the edges set into matchings. And the chromatic index is the minimum number of matchings which decompose the entire edge set. So here we have a hypergraph with chromatic index 3, and each of the color class form a matching, which together decompose the entire edge set of the hypergraph. And it is known to be NP hard to determine the chromatic index of a graph. So basically, it is difficult to determine the chromatic index. So people instead study how to approximate the chromatic index in terms of some easily computable parameters. So I would like to define some basic local parameters in hypergraph. So a degree of a vertex is a number of edges containing the vertex, and the maximum degree is a maximum of the degree of the vertex, and denoted by delta. And a co-degree of the pair of distinct vertices is a number of edges containing both. And the maximum co-degree is the maximum of the co-degree of every pair, and delta 2 stands for the maximum co-degree of the hypergraph. And there is a classical result by Bissing in 1964 who showed that the chromatic index of a graph is between the maximum degree and the maximum degree plus the maximum co-degree. So if maximum co-degree delta 2 is sufficiently smaller than delta, then this theorem gives quite a good approximation for the chromatic index of a graph. So one may ask, what happens if delta 2 and delta are similar? And there is a conjecture by Goldberg and Seymour in the 1970s, which states that for any graph G, the chromatic index is at most the maximum degree of +1, or some ceiling of some density function defined here. And in fact, it is easily checked that this density function is a lower bound for this chromatic index. And in particular, it implies that the chromatic index is either the ceiling of some chi f prime g and ceiling of chi f prime g plus 1, where a chi f prime g is a fractional chromatic index of g, which is a linear programming relaxation of the chromatic index. And it is defined by the maximum of maximum degree and this density function for a graph. So this actually gives a very good approximation on the chromatic index of a hypergraph of a graph. And in 1996, Khan showed that the chromatic index is actually roughly equal to the fractional chromatic index asymptotically. And there's many results which improves this Khan's result quantitatively by replacing the delta plus 1 here with delta plus some sublinear term in delta. And in a few years ago, Chen, Jing, and Zhang, they announced a proof of the conjecture, but the proof is highly complicated. And very recently, in arXiv, the short proof of the Goldberg-Zimmer conjecture appeared. And the authors are Chen, Hao, Yu, and Zhang. So this is the result for the proper edge coloring of graphs. And let me mention some known results for the edge coloring hypergraphs of bounded rank, where the rank means the maximum size of the edges. And we have the trivial bound here. So the chromatic index should be at least delta, which is a maximum degree, because if you consider a vertex achieving the maximum degree, and if you consider the edges containing the vertex, then such edges intersect each other, so they receive different colors, so the chromatic index should be at least delta. On the other hand, for each edge, there are at most k vertices inside the edge. And for each vertex inside the edge, it has a degree delta, including the edge itself. So this is basically the upper bound for the number of edges intersecting a given edge plus 1. So this is basically the obvious upper bound we have for the chromatic index. And in 1989, Pippenger and Spencer proved a kind of the analogous result for the Bayesian theorem for graphs. So given any hypergraph with a rank bounded by some constant k, and if the maximum degree, if the maximum co-degree is sufficiently smaller than the maximum degree, then the chromatic index should be close enough to the maximum degree. So the Pippenger and Spencer theorem states that if the co-degree is sufficiently smaller than maximum degree, then the chromatic index is close to the extreme on the left here. And there are several improvements of this Pippenger and Spencer theorem. So in 1996, Khan proved a least variant of the Pippenger and Spencer theorem, such that the same conclusion holds for the least chromatic index, which is a slightly general than the chromatic index. And Molloy and Reed, they were able to improve this epsilon here quantitatively in terms of the maximum degree and co-degree for the least edge coloring. And very recently, we are able to improve the Molloy and Reed result quantitatively for non-leaf edge coloring. So the Pippenger and Spencer result is one of the very earlier result based on the semi-random method called the Nibble method in probabilistic combinatorics, which is now a standard technique. But what if delta is similar to delta 2? Then the Pippenger and Spencer theorem doesn't say anything. For those cases, there is a conjecture by Khan, show that if Khan states that if the hypergraph has a rank bounded by k, then the chromatic index should be close to the fractional chromatic index asymptotically. But unlike for graphs, so for graphs, we have a very easy characterization on the fractional chromatic index. But for hypergraph, there is no simple characterization on the matching polytope. So the main difficulty lying on this conjecture is there is no simple characterization on the fractional chromatic index. So far we dealt with some edge coloring result for hypergraph with bounded rank. So the natural candidate to consider is an edge coloring hypergraph of unbounded rank. So as I mentioned, Pippenger and Spencer theorem roughly state that the chromatic index is close enough to the maximum degree if both rank and the maximum co-degree is sufficiently small, smaller than the maximum degree. And one may ask if the similar phenomenon hold if we drop the assumption on the rank. But however, we do not. So for prime power k, there is an example of the finite projective plane of order k, which is an intersecting hypergraph on n vertices and n edges, where n is roughly the quadratic in k, such that every edge has size k plus 1, which is roughly square root of n, and it has maximum degree k plus 1, which is also square root of n, and the maximum co-degree exactly 1. However, the chromatic index is much larger than the maximum degree here, which is exactly n. And actually, it matches the bound on the right extreme of the trivial bound. So we have a very limited understanding on how to color edge-colored hypergraph of arbitrary length. So here's a conjecture by Erdos-Faber-Lovasz in 1972 regarding edge-coloring linear hypergraph of arbitrary length. So the linear hypergraph means the hypergraph with maximum co-degree at most 1, which means that for any pair of the vertices, there's at most one edge containing the pair. So the conjecture is stated as follows. So every linear hypergraph H on n vertices with maximum degree at most n should have chromatic index at most n. So the chromatic index is bounded by the number of the vertices. So in fact, this statement is not the original statement of Erd and Faber-Lovasz. So the original statement of the Erdos-Faber-Lovasz is written in terms of the coloring nearly disjoint union of the complete graphs. So we are given with n complete graphs, G1 and G1 to Gn, such that each complete graph has at most n vertices. And for any pair of the complete graph, it has at most one vertex in common. Then the chromatic number of the union of those complete graphs is at most n, which means that we can color the vertex set of the union of the graph in n colors such that no two adjacent vertices receive the same color. So to see why the both statements are equivalent, we may consider the line graph, LH, line graph of the hypergraph H, whose vertex set is equal to the edge set of the hypergraph, and two edges in the hypergraph are adjacent in the line graph if and only if they are intersecting each other. And if we, for given an ith vertex of the original hypergraph, if we collect the edges of the hypergraph containing this vertex, then because they contain ith vertex, so those edges intersect each other, so they form a clique in this line graph. So they are actually a complete graph. So those collection of the edges correspond to the complete graph here. And the size of this collection should be at most n, because the size of this collection is exactly the maximum the degree of the ith vertex. So it is bounded by n from this assumption. And the intersection of the vertices in Gi and vertices in Gi is at most 1. And this statement corresponds to the linearity here. And this bound on the coloring correspond to the chromatic index. So this is why both statements are equivalent. And so one of the difficulties to attack this conjecture is that we need to describe a proof incorporating those three well-known examples, extremal examples with very different shapes. So those three examples have chromatic index exactly n. So the first example is a finite projective of order k, which is a k+1 uniform intersecting hypergraph with n vertices and n edges. And the second example is a near pencil, which is an n vertex intersecting linear hypergraph, which consisting of n minus n edges of size 2 and one single edge of size n minus 1. And the final example is a complete graph with odd number of vertices. So this is the only example which are not intersecting hypergraph among those three examples. And there are some special cases we can consider. So if our hypergraph is graph with linear graph, then one can show that it has maximum degree at most n minus 1. So Ising theorem show that the chromatic index is at most n. And if we consider the linear hypergraph on n vertices, where every edge has size between 3 and k, where k is some fixed constant, then one can show that the maximum degree is at most n over 2. And this is a proof by a figure. And the chromatic index, by Pippen-Spencer theorem, the chromatic index is at most n over 2 plus literal n. So this is much smaller than n when n is sufficiently large. So, but here you can see that the size 2 is excluded. So it was not even known whether the conjecture is true for any linear hypergraph with bounded rank. And there are so many partial progress for this EFL conjecture, so I would like to mention only a few of them. So the first result is the result by De Bruijn and Erd H in 1948. So they show that every linear intersecting hypergraph on n vertices has n edges. So because it is intersecting, its chromatic index is at most n. And they actually characterize the linear intersecting hypergraph on n vertices and n edges, such that the only examples are either a projective plane or the near pencil if we exclude the edges of size 1. And we can see that this result appeared earlier than this conjecture, so I think the result by De Bruijn and Erd H is actually one of the motivation of the conjecture by Erdos-Faber-Lovasz. And if this statement is true, then we have a chromatic index at most n, which means that we have n matchings which decompose the entire edge set. So by averaging, if this statement is true, then we have a matching of size, at least the number of edges divided by n. And this weaker statement is proved by Seymour in 1982. And in 1992, Kang and Seymour showed that the fractional relation of this conjecture is true. And these two results are based on the Nibble method, which is now a standard semi-random method technique in probabilistic combinatorics. And so in 1992, Kang resolved the conjecture asymptotically. So he showed that the chromatic index is at most n plus literal n. And very recently, Faber and Harris, they confirmed this conjecture to be true if we restrict every edge to have size between 3 and some small epsilon times square root of n, where epsilon is some small absolute constant. So very recently, we are able to prove the EFL conjecture for any sufficiently large linear hypergraph. So if n is larger than some n0, which is an absolute constant, then every n vertex linear hypergraph with maximum degree at most n should have chromatic index at most n. And one may ask, if we assume some further assumption, can we improve this chromatic index a bit? And there are some natural substructures which force the chromatic index to be close to n, or a vertex of degree close to n, because if you consider the edges containing this vertex, then those edges are pairwise intersecting each other, so the chromatic index should be at least the maximum degree. So one of the substructures forcing the chromatic index to be close to n is a vertex of degree close to n. And another substructure which force the high chromatic index is some structure which is similar to a projective plane. So if we have roughly n edges of size close to square root of n, then we can deduce that most pair of the vertices are contained in one of those edges, and most pair of those edges intersect each other. So if you consider the line graph of this substructure, then it is quite close to the complete graph. So it is likely that they have a high chromatic index. So another result of our paper is that if we forbid any vertex of degree close to n, and if we assume that the number of edges of size roughly square root of n is slightly below n, then actually we can improve the chromatic index from n to n minus some sigma n for some small sigma, where sigma is some constant which is the linear in delta. So there is a question by Erd H after the conjecture by Erd H and Faber-Lovasz in 1972. So he asked the kind of a higher co-degree analog for the Erd H-Faber-Lovasz conjecture. So he asked, what is the maximum chromatic index for n-vertex hypergraph H with maximum degree at most n and the maximum co-degree at most t? And so when t is equal to 1, then this coincides with the EFL conjecture. And Horag and Tusa in 1990, they show that if t is larger than n to the 1/2, then the nth is asymptotically n to the 3/2. And another result of ours answers the Erdős question for this range of t, where t is between 2 and square root of n for infinitely many n, where there is a projective plane of n vertices. So the statement is as follows. So if H is an n-vertex hypergraph with maximum degree slightly below t times n, and the maximum co-degree at most t, then the least chromatic index is at most tn. So we sacrifice here epsilon tn from the maximum degree, and then we obtain some stronger result on the least chromatic index instead of the chromatic index. And we also characterize when the equality holds. So if the least chromatic index is exactly tn, then we have a unique extremal example, which is that the hypergraph, which is a union of t identical copies of a projective plane of order k, where n is k squared plus k plus 1. So considering the case when t is equal to 1, so it gives the result that if we forbid any vertex of degree close to n, then the unique extremal example for the EFL conjecture is a projective plane. So for the remaining time, I would like to briefly overview the proof ideas. And so far, any questions? Great. So this is our result. And our result consists of two steps. So the first step is to color all the large edges with n colors. And to color all the large edges, we analyze the structure of the line graph of the sub-hypergraph consisting of large edges. So in this step, our key lemma is called the reordering lemma. So we are able to find some linear ordering on the large edges such that either we can color the edges with n minus tau n colors greedily for some small constant tau, or we can locate some dense subset of the edges with some structural properties. Either it is close to being a projected plane, or its line graph is locally sparse, so we can efficiently color the edges in this case. And the second step is extending the coloring from step 1 to color the remaining small edges using n colors. And this is based on some semi-random approach, the Nibble method. And we are able to extend each of the color class so that it includes all the high degree vertices, thanks to some result on pseudo-random matchings. And after doing that, we can color all the edges of size at least 3. So the remaining uncolored edges are the edges of size 2, so that we can color them using some well-known results in graph theory, such as a Ising theorem. So basically, our proof boils down to using some well-known graph coloring result at the very end. So let us discuss the proof idea for the first step. So let us assume that every edge of our hypergraph has size at least r, where r is some large constant, and consider any linear ordering on the edge set of the hypergraph, and let the ordering E be the number of edges intersecting and preceding this edge E in this ordering. So as in this figure, we have a linear ordering here, and we call this a forward degree of this edge. And one of the easy observation is that the chromatic index is at most the maximum of the forward degree plus 1. So why this observation is true? Because we can greedily color from left to right, sweeping the linear ordering we have. And in order to color this edge, we see all the colors used in these neighbors in the forward degree. And we can use the color difference from all the colors here. So we have plus 1 here. So it would be very nice if you're able to find some linear ordering with this maximum value is at most n minus 1. And one of the observation is that for any edge E, there are at most this many edges of size at least the size of E and intersecting E. So because this R is large enough, this is very close to N. So the proof is quite simple. So if you consider any vertex in this edge and let E itself and F1 to Fn be the edges of size, at least size of E containing V, then by the linearity of H, we deduce that if we delete the vertex B from each of the edges here, then they are actually pairwise disjoint. Because otherwise, if they consider some vertex W in Fi and Fj, then they contain both B and W, so it violates the linearity condition. So they are pairwise disjoint, subset in the VH minus V. So we deduce that this n plus 1, the number of edges here, the number of subsets here, is at most n minus 1 over the size of E minus 1, because F1 to Fn has size at least E. So because the vertex here is arbitrarily, and they're exactly the size of E many vertices in E, so we multiply the size of E here, so we obtain this quantity. So by using observation 1 and 2, we have a following corollary, such that the chromatic index of this hypergraph consisting of large edges, at least R, is less than 1 plus 1 over R minus 1 times n by taking the linear ordering in decreasing edge sizes. So as you can see, so if R is sufficiently large, then we have a quite good bound on the chromatic index. But to achieve the bound at most n, we need some different strategy. So basically, so we start with some linear ordering on the edges in decreasing edge sizes. Then if every edge has 4 degrees, less than 1 minus tau times n for some small tau, then we are happy because by the observation we discussed earlier. Otherwise, we are get stuck at some edge, E star. So E star is the last edge in the ordering, which violates this inequality. So this is the last edge with the 4 degree at least 1 minus tau times n. Then all the edges after this E star should have 4 degree less than 1 minus tau times n. And we want to slightly modify this linear ordering by enlarging this set of edges. So how to do so? If there is some edge f which appear earlier than E star, such that if it intersect less than 1 minus tau times n edges, which precede E star, then we can move this f right after E star without violating this condition. So we keep moving and moving to enlarge this latter set so that we can deduce that every edge f appearing before E star intersect at least 1 minus tau times n edges preceding E. And the edges after E star have 4 degree less than 1 minus tau times n, and for any edge f here, it intersects at least 1 minus tau times n edges in this side. And so if we consider some edge f, which has size close to the size of E star, then what happens? So if we choose tau sufficiently small, then in the observation 2, we know that there are roughly n edges of size at least the size of E intersecting E. And in this case, this f has a lower bound very close to n. So this f, which appears before E star with the size of f close enough to E star, behaves like a kind of the extremal case for this observation. And if we analyze this proof further for the extremal case, one can deduce that most of the pairs of vertices U and V, where U lies in F and V lies in outside of F, are contained in one of the edges of size very close to F. So if we collect all the such F of size close enough to the size of E star as W, so W is a collection of the consecutive edges here, with size close enough to size of E star, then we can deduce that this collection of edges is very dense, which means that for most of the pairs of the vertices in this hypergraph, there is an edge in this collection which contains both. So this is our main observation of this reordering. And we obtain the following lemma, which is called the reordering lemma, which roughly states that either, so we can find a linear ordering such that either 4 degree of any edge is less than 1 minus tau times n. So in this case, we are very happy. And the latter case, if we get stuck and by moving some edges and collecting the edges of size close to the size of E star, we obtain a dense subset where the ordering of the edges, so W appears, so this is H prime. H prime is the set of edges consisting of the edges prior to this edge E star, and we have, so this dense W satisfying this ordering. And one of the nice part of this lemma is that actually we can iterate this lemma. So for example, so we have this nice part here. After applying this reordering lemma, we have this nice part and some dense part here, and still we don't know about the left side of this dense part. And we can apply this lemma for this left part so that either we have a good ordering here or we have a dense part here. But we cannot have disjoint two dense part in both parts by the definition of denseness. So denseness means that the most pair of the vertices, for most of the pair of the vertices, there is an edge containing in the set. So we cannot have dense part, which means that for this left side here, we only have this first condition. So we can deduce that by reordering this part, the left part is also good. And another remark is that by analyzing the proof of the reordering lemma, actually the proof works for any tau, not only just for the small enough tau, for any tau between 0 and 1. And if tau is close to 1, such as a 1 minus 1 over 1,000, then we need to relax this dense condition for here the not most, but some positive fraction of the pair of the vertices. But anyway, yeah, we can prove the reordering lemma for any tau between 0 and 1. So by applying this reordering lemma at most 2 times, we deduce the following corollary. So we have a linear ordering on edge set. Either the 4 degree is less than 1 minus tau times n, or we can locate some dense part of the edges. Either W is close enough to being a projective plane, or the line graph of this dense part is locally sparse. And if this dense part is close to being a projective plane, which means that these edges, the size of the edges in this dense part is roughly square root of n. And by the construction of our linear ordering, so for this H prime part, the size of edges here is at least the size of the edges in this dense part. So this part also has in this part, edges also have size at least square root of n. So 20 minutes. Okay, 5 minutes. So in this case, in this case we deduce that the H prime, every edge of H prime has size roughly at least square root of n. So we can use this lemma, which we proved in our paper. So the main idea of this lemma is that this lemma is has a kind of ad hoc proof. But if you assume that the every edge has size roughly square root of n, then the number of such edges should be quite close to n, which is n plus some delta n for sufficiently small delta. So in order to reduce the chromatic index to be at most n, we need to find find some pairwise, some pair of disjoint edges. So yeah, so that's a kind of the intuition behind of this lemma. And if the latter case hold, then we can use some well-known result on decoloring the locally sparse graph. So G is zeta sparse if and only if neighborhood of each vertex is far from being a clique of size delta. And we use the well-known result by Molloy and Reed. So if the number of edges, so if G is zeta sparse, then the chromatic index is at most delta minus zeta over e to the 6 times delta. So it is slightly below the trivial bound delta plus 1. And the study of coloring the locally sparse graph is initiated by Molloy and Reed in 1997, when they attempt to make progress toward the famous Erd necessary conjecture on strong chromatic index. And there are some results improving this constant. And very recently, a group of authors proved that if we replace zeta over e to the 6 by any constants below this, then we obtain the same conclusion. And this is almost best possible because the zeta over 2 is best possible for sufficiently small zeta. And on the extreme case, when zeta is close to 1, then there is a result by Alon Kravich and Sudakov. And this is initiated by Johansson regarding coloring triangle-free graphs. And yeah, there's a series of results regarding the coloring locally sparse graphs. So let me skip this part and let's consider the open problems. So there is a generalization of the edge coloring, so which is called the least edge coloring. So we are given with a set of lists for each edge, such that, so the list means that the list of available colors for each edge. So L edge coloring for a given list L is a proper edge coloring such that every edge E should use a color in this set of available colors given for E. And the least chromatic index is that the minimum K such that there is a L edge coloring of H for any list with list size exactly K. So it is obvious that the least chromatic index is a upper bound of the chromatic index. And Faber conjectured that the least variant of the EFL conjecture. So any n-vertex linear hypergraph has least chromatic index at most n. And there is a result by Khan, which is stated that the least chromatic index is at most n plus liter of n. And our proof showed that if our hypergraph consisting of large edges, which have size at least some large constant and any sufficiently large, then the conjecture is true. But it is still open even when you assume all the edges to have size at most some large constant. So one of the issue for this result for this conjecture is that we do not, so when we color the small edges at the very end, we use a kind of the well-known graph coloring result such as a Bising theorem, but there is no analog of Bising theorem for the least edge coloring, so there are many issues for proving the case when H is HS bounded rank. So I think time is out, so this is the end of the talk. Thanks for attention.
Thank you very much. Are there any questions? Okay, well, if there's no questions, let's thank our speaker again.